record this. So at this point, you should have in your mind that things. First of all, let's kind of do a quick review, and you should have in your mind. I guess I should do it this way, right? So you should have in your mind, when you're reviewing that intermolecular forces determine the melting point, freezing point, and the evaporation point, condensation point, right? These two are the same. That's a degree, there's a temperature. At this point, you should understand that temperature is a measurement of average kinetic energy. There should be a good understanding of that. At this point, when you're talking about what we've talked about so far, you should understand that hydrogen bonding, though weak when compared to covalent bonds, are strong intermolecular forces. That these things pull on each other, and sometimes the forces sometimes the forces in a system can oppose each other, and it's the balance of those forces that can then determine the outcome. So the example we looked at was the balance between the kinetic energy, and this is the idea of kinetic energy, the kinetic theory. Let me go ahead and write out kinetic. The kinetic theory of molecular action. So when you're looking at how molecules act, how they move, there's this idea that its kinetic energy can help explain that. It's one of the things that help explain it. The other thing that helps explain it is this intermolecular force. The forces in between molecules that help determine whether they stick together or not. All right, so this force right here and kinetic energy are the two things that kind of help us understand how to predict what's going to happen when you're mixing molecules together, or when you're looking, for instance, next week we're going to start talking about cells. I think it's next week. We'll have to look at the calendar again. But we'll be talking about cells and how do things get across a cell? How do things go from your blood into your brain? How do things go from your brain cells into the blood? So how do these things move? And that has to really do with two main ideas here, and that's this idea of kinetic theory, and another concept, that we're talking about here is this intermolecular force, right? So the energy that the molecules have that are given to them by heat, remembering heat is how kinetic energy is transferred. All right. There's a ton of things you should think about how is heat transferred, and hopefully you learned about it in physics or physical science in 8th grade or whatever it is that you took. All right, so let's move on then. Now we have that, and we also have an understanding of water, another part of the review, and maybe I shouldn't put a whole line there. Maybe it should just be kind of a dash line here. Another part of this is water, and we looked at water's ability to, we said water's sticky, and we said there's cohesion, and then there's adhesion, right? Where adhesion is in water sticks to other things. And cohesion is when it sticks to itself. And it's the stickiness that makes, and what is the stickiness? It's intermolecular force, right? When we say sticky, we're really talking about intermolecular force. And that intermolecular force specifically is hydrogen bonding. That's when we're talking about water, and a lot of the biomolecules we'll be talking about. This includes DNA, proteins. Hydrogen bonding is the thing that we got to consider. All right. So water itself is very sticky, and that's because of intermolecular force. We know that water has an ability to take in a lot of heat and not increase temperature. We looked at that in the graphs, and we said, all right. So what do we call that? That ability to take in a lot of heat and increase and not increase temperature. What do we call that? Do you remember? Do you have it in your notes? It's in your notes. I put it up in the board. This is a good chance for you to, this is a reflective moment where you can go look and see, did I write it down? Say again? Ethanol was an example of something that was less polar. It's something that it's the definition, something whose definition is the ability to take in heat and not increase temperature, to keep a stable temperature. There's a measurement of that. We said water has a high this. And we said that's why when we live in Cleveland, the temperature in Cleveland is more stable than the temperature in Columbus, or the temperature in New York, New Jersey, etc. on the coast is more stable than when you go inland, because you have the ocean, you have the Great Lakes. Yes. Yeah. No, the lower boiling points does have to do with intermolecular bonds, but the term was specific heat. And see, the term itself has to do, the ability to take in a lot of heat. The ability to take in a lot of heat, and the term is specific heat. Right? So the ability to take in a lot of heat and stay a stable temperature is what we call specific heat. The exact definition would be the amount of heat that must be absorbed or lost for 1 gram of a substance to change 1 degree Celsius. Do you really want to memorize that? So, it's a good definition. It's real simple, but it's just a lot of words. So all I'm saying is when you're looking at specific heat, some things can take in a lot of heat and not change temperature. Now let me ask you something. It's a sunny day. And you're going out to play basketball. Okay? There's a pond right next to a basketball court. You're barefoot on a hot sunny day. You walk onto the, I don't know, you're a little kid so you don't know better. You're walking on the basketball court. What's going to happen? You're going to burn your feet. So what are you going to do real quick? Go to the pond or lake and dive in. What's the pond or lake? Yeah, but what is it? Cool, hot? It's going to be cooler, right? Cooler than the blacktop.
Right.
Why? Because the water can absorb the same heat. It's that heat that's in that blacktop is the same heat that the water got. But the blacktop is a lot hotter, isn't it? The temperature of the blacktop is a lot higher. The water is not as high. It has the same amount of heat, but it's not as high. Why? Because water has a higher specific heat. It can take in a lot more heat and not change temperature. Something like blacktop and concrete, that stuff is going to absorb heat. Now, concrete's better than blacktop. And there's other things involved with that, so I'm really oversimplifying and possibly even misdirecting because there's other factors that I'm not going to get into right now with the blacktop and that has to do with albedo and absorption, etc. But the bottom line is that the specific heat of water allows water to stay stable, even. Now that's important for life, isn't it? If you're going to stay a stable temperature, you don't want to go out in the sun and start boiling. Your temperature go up to 102 because it's 102 outside, right? And you don't want to go. How you doing? You okay? Was there a nurse?
She might as well kick me out because she knew.
Well, I told you she's not good. It's not her fault. There are laws. We can't treat you unless you're a physician, and even a physician has to get permission from your parents. So we can't give you medicines. We can't give you a treatment or anything like that unless there's a written prescription that says, please give my daughter this medicine, and then there has to be a doctor's note. It's all kinds of crazy stuff. And it's good reasons for that, right? If they gave you a Tylenol because your neck hurts, and then you end up being allergic to Tylenol and get sick, it's the nurse's fault, right? She doesn't know. And neither do you, maybe your parents don't even know. So it's not fair to put her on the spot and ask her to give you medicines. That's why I said you can go and ask, but I didn't think there was much going to happen. So specific heat, the ability to take in a lot of heat and not increase in temperature. Very important for life. Very important for stabilizing the temperature of the environment. Very important for life to have it can continue to stay stable as well. Then there's this other term. You're going to have to know these, so that's why I'm going through them. There's another term that's called heat of vaporization. What do you think this is? Right. Go ahead. It's about evaporation. Yeah. So what about it? How would you define it? Give me a definition. Heat of vapor. The terms in the words actually give you the definition if you think about it. What is heat of vaporization? What could it possibly mean?
Probably when you was talking about the lake and it absorbed all the heat from the hot, so it keeps it a little cold.
Well, that would be heat, specific heat, right? So that's specific heat. That's good. Now we have the word heat of vaporization.
Like when there's steam, like how hot it might be.
Good guess. Excellent guess. It's how much heat is necessary to evaporate 1 gram of water. That's kind of easy, right? How much heat does it take to evaporate stuff? Do you think water has a high heat of vaporization or a low one? as compared to alcohol? High as compared to alcohol, right? Because water has hydrogen bonding. Remember, what does it take to change phase from liquid to gas? You have to break the hydrogen bonds. Where alcohol has hydrogen bonds that are much weaker. Where you look at nonpolar stuff like oxygen, its heat of vaporization is very low. It's negative 100, 800 and something. Negative 183. Something like that. So water's heat of vaporization is 100 degrees Celsius. That's much higher than oxygen. Agreed? Agreed or not? We understand this? If you don't understand it, there will be a test soon, and you need to know it. So now's the time to ask a question. Repeat what? The heat of vaporization? It's on the board. It says, how much heat is necessary to evaporate 1 gram of water? So if I have a gram of water, how much heat do I need to evaporate that? I need at least if you indirectly say temperatures related to heat, then you'd have to say 100 degrees Celsius, right? We don't measure heat that way, but let's just say 100 degrees Celsius. So that's higher than alcohol because alcohol is 70 degrees. Now that's not a measurement of heat. It's going to take a lot of heat to get water to evaporate because you got to get this stuff to 100 degrees Celsius. The alcohol, the same amount, 1 gram, you only have to get it to 70 degrees Celsius before it starts evaporating. So it's going to take less heat to evaporate alcohol than you would water. Do you agree? Same with oxygen. Oxygen, you only have to get it to negative 183. You don't even have to add fire to make oxygen gas. It comes as gas at room temperature. In our environment, anything you are going to experience, oxygen is going to be gas. It's never going to be a liquid on the surface of the earth. The surface of the earth doesn't get to negative 183. It just doesn't get that cold. Negative 40, negative 50, yeah, but not negative 180, right? So the surface of the earth will never have frozen or liquid oxygen. So we understand what I'm saying? Because some of you seem like you're tired. I'm not sure what's going on, but I'm going to go on. I have to give you these definitions, otherwise how are you going to get them? So what about evaporation? How do things cool? We have something called evaporative cooling. Look at the words, people, and put context clues. Consider what we've been talking about. Ladies having a conversation back, please pay attention. So evaporative cooling, the answer, can we get our book bags off the tables? I like to see you. It's so hard to see you through all these book bags. So heat or evaporative cooling, what does that mean? Think about all the things we've been talking about. Water, we've been talking about phase change. What would evaporative cooling mean? I forgot to get the canned air. I'm going to have to bring it in for tomorrow. Yeah? Go ahead.
The temperature it takes to make something cold.
I like it. Good try. Good guess. So that gets to the cooling and temperature. But what's this word mean, evaporative? It's going to evaporate, right? So this is not a measurement, but this is a process. And you do it all the time every time you sweat. And I gave you an example of this yesterday. I said, and I wanted to bring the canned air, but I forgot to bring it. So you have this canned air, and it looks something like this. Horrible drawing, but that'll do. And it starts to spray. Here it's a liquid. This is a gas. We understand that? Liquid to gas. What is that called? Evaporation. Now, this evaporation is happening because I'm releasing pressure. It's liquid in here because of the pressure. And if I release pressure, then by pushing on the little knob, it turns into gas because there's less pressure. That's easy. But remember what we talked about yesterday. You have to be able, if you're going to go from a solid, I'm sorry, that's not right. If you're increasing temperature or something, in order to go from a solid to a liquid, you need energy. And to go from a liquid to a gas, you need energy. Remembering that this would be liquid here, and this would be solid down here, and gas up here. Please look at the chart. Please try to focus. Please try not to have side conversations. Please try to think about what I'm saying here so I'm not going to give you questions like define heat of vaporization. You're going to have to apply the knowledge to new situations. So you have to be able to understand the process. That's the key. That's why we do labs. That's why I have you answer and ask questions. That's why participation in class is going to help you. So what we're talking about here is there's this energy required to change phase from liquid to gas. So this can is liquid here and it's gas up here. This is air. They took air and put pressure on it and made it liquid. Now it's liquid. Liquid oxygen, liquid nitrogen, liquid, all these things, it's all a solution of liquid. You press on this, out it comes. What happens to this can? I described it yesterday. It gets very cold. It gets very cold. In fact, so cold that any water in the air forms crystal or ice on the outside of the can. It gets very cold, and you'll see it when I bring it tomorrow. I forgot to buy it last night. I have to go to the store today anyway, so it makes sense to do it. So that can will actually have ice form around it, and the spray itself is very cold. These molecules are very cold when you. So this is getting cold. Why is it cold? Why did it get cold? Yeah.
The molecules of it just lost their kinetic energy.
Actually, yes, the cans. So this is very tricky, right? The way you're phrasing it. But you're right. The cans molecules lost kinetic energy. So the metal can lost kinetic energy. Where'd that kinetic energy go? Where'd that kinetic energy go? Into the air out here?
No.
Into the liquid, right? So what happens is that when you're getting this phase change, the heat, let's call it heat, the change in heat, is going into the liquid from the environment. If you're touching the can, it'll be your hand. If you're not touching the can, it'll come out of the air and the can around it. Everything around is going to get colder because the heat that it has, the kinetic energy it has, the heat that it has, the energy, is going to transfer into the liquid so that the liquid then can change from liquid to gas. It needs this much energy to do that. That's evaporative cooling. By liquids evaporating, it takes the heat off the stuff that it's touching. By the way, that's how air conditioners work. That's how your refrigerator works. Your refrigerator and your air conditioner have a compression pump. It compresses the air. Then it's a liquid. And then it pushes the liquid through coils. As the coils come into contact with the warm air outside, the heat from the warm air outside the refrigerator, or in the case of the refrigerator, inside the refrigerator, in the case of the air conditioner, the heat inside your house circulates around these coils. These coils then absorb the heat. The liquid turns into gas, which then goes outside of the air conditioner that gets compressed again with electricity, and the excess heat gets pushed out to the outside. That's if you've ever touched the air on an air conditioner on the outside, that air is hot. That's the heat is being transferred from inside the house to outside the house. The heat in the refrigerator also is taking the heat from inside the refrigerator and pushing it into the kitchen. So that's how you can't get rid of heat. You can't destroy it. You got to move it. And the way it's doing it is by evaporation. You do it when you have an arm, and you're hot, and you sweat, you start to sweat. What you do is you put little droplets of water. By the way, it's not just water. It's water and salt and urea, the same stuff that's in your urine, right? All comes out of little droplets of sweat. That's what's in sweat. Do you ever notice that sweat can turn your shirts yellow? That's urea. Urea salt. It's not nasty. It's part of who you are. It's coming out of you. Nothing that comes out of you is nasty. It's part of nature. So you need to, and I know it's hard for us to understand because we don't like to play around with urine, but the reality is that you sweat urea. And urea is not urine, but it is the main component of urine. So you start to sweat through your sweat glands, and you got this little beads of sweat. Well, if you're able to evaporate, what happens is that the heat from your body gets transferred into the water. And what happens to that water? It evaporates. By evaporating, the water then, not only does it take the heat from that to increase its own kinetic energy, then it also uses up the phase change energy, so you get a lot of heat being removed. That's called evaporative cooling. You're cooling yourself because the heat that's in your body is going into the water that then is evaporating and going away. It's taking it off into the air. That's how you cool off. If you ever walked wet in front of a fan, if you've ever sweat outside or in the gym or whatever, and you're just really tired, you sit in front of a fan, what happens to you? You cool down, you get cold. You just don't cool down, you start to get cold. That's because there's a lot of evaporation. In front of that fan, you got to start getting a lot of water going into gas, and that's taking a lot of heat with it really fast. So that's called evaporative cooling. Evaporation is one way of cooling, and many creatures do this. Plants do it. Plants do evaporative cooling. Dogs do it when they're panting. Their sweat glands are in their mouth, so they're evaporating the water from their mouths. Also, they have some sweat glands in their paws. Not all creatures do evaporative cooling. Desert animals, for instance, and desert plants try not to do evaporative cooling. That makes sense because there's not a lot of water, right? But a lot of creatures do. We talked about water freezing and floating on ice and why that's important. Now, the next section is going to be the next thing about water is going to be important for tomorrow's lab. And I'm going to give you your pre-lab here, and you're going to take notes on it. I'm not going to print it out because I didn't have a chance to type it up last night. So we're going to write out the pre-lab today. We're going to write out some ideas, and I'm going to post some notes for you on Schoology. It's going to be typed up, PowerPoint-like. It'll be in a PDF, but it'll be PowerPoint-like notes. It's going to walk you through the background, okay? I'm going to walk you through it now. You'll have some backup on your PDF on Schoology, and tomorrow we'll do the lab, okay? Yeah. Do I have a pencil? No, I'm sorry, I don't have one. Do I? Sorry, does anybody have an extra pencil? You got one? I thought maybe. I know I have some extra pencils. I have like a bunch of pencils I put aside. All right, well, I don't know where they are, so let's move on. All right. So I guess if we're going to go ahead and write a summary here, I'm going to let you write the summary on all this. This all has to do with reviewing some of the things we talked about, specific heat, this is new, and heat of vaporization. Well, specific heat is also reviews. Heat of vaporization, evaporative cooling, I think you agree it's kind of an adaptation or an application what we talked